Okay, here we see a little question from the 2013 practice exam, and the student is given the task of determining the enthalpy of a reaction for the reaction between hydrochloric acid and sodium hydroxide. And you should immediately jump for joy because we did this lab, enthalpy of neutralization. A couple things you should remember: we mixed all those different acids and bases in our coffee cup calorimeters. They were exothermic. Temperatures went up, and no matter what kind of acid and base we mixed, they were all somewhere around like negative 50 kilojoules per mole. I'm sure you remember all that. But anyway, you see the following materials. You got 1 molar and 2 molar for each acid and base, distilled water, goggles, gloves, and lab coat, safety first. Our insulated cups, coffee cups with covers. We got a thermometer that goes to the 10th of a degree Celsius, and a stir rod. And we've got some glassware, Erlenmeyer, beakers, graduated cylinders, and there's some precision that goes with that. So again, remember, Erlenmeyer flasks and beakers we predominantly run reactions in. Graduated cylinders, burettes, pipettes, that's what we typically measure with. So part A here, the student selects two 100 ml beakers and measures the 50 mils of the 1 molar solutions. Not very good. Measures an initial temperature of 24.5 degrees Celsius, pours the mixtures together, covers cup, and we do see that the temperature goes up to 29.9. Is this experimental design sufficient to determine the enthalpy of a reaction to 2 sig figs and justify? Not with beakers. The beakers are plus or minus 10 milliliters. So when he measures or she measures 50 mils of the solutions, that's anywhere between 40 and 60. That's only 1 sig fig with those beaker measurements. So that is not going to give us justification for the enthalpy to be to 2 sig figs. So definitely no. What are 2 changes that will allow the student to determine the enthalpy of reaction to a precision of 3 sig figs? Well, we need 2 changes. So first of all, the graduated cylinders that go to the 10th of a milliliter precision-wise, that will give us 3 sig figs. And then you got to think of something else. We're going to have to do Q equals MC delta T. So when we mix the solutions together, 50 of each, 100.0, that would give us 4 sig figs. And then C is a constant, so delta T, right now 24.5, 29.9. That's like a 5.4 degree temperature change. I would need that to get to something that had 3 sig figs. And so when you look up here, if I double the concentrations, that would double the amount of heat released. So that would be the second thing that I could do in order to get to 3 sig figs. So definitely use the graduated cylinders, and then if I use the 2 molar, I would get a larger temp change. So the 1 molars gave me 5.4 degrees, 2 molars should be over 10 degrees. Now that's a tricky point to get, but remember, heat release depends on how much. Okay, so if I put a little bit of stuff in the reaction, I'll get a little bit of heat because it's per mole. If I put twice as much, double the molarity, I'll get double the heat, and I would get double the temperature change. Tricky point, but one you can get. A second student is given 2 solutions. We've got our 1 molar hydrochloric acid and sodium hydroxide again, this time 75 mils of each, 3 sig figs in all those measurements, and 25 degrees Celsius. Again, 3 sig figs, just mentioning. Pour the solutions into the insulated cup, stir, cover, records the maximum temperature, blah, blah, blah. Student calculates the amount of heat evolved in the experiment to be 4.1 kilojoules. Calculate the experimental value for the enthalpy of reaction in kilojoules per mole. So if you remember when we did this in lab, it doesn't matter whether or not we use hydrochloric acid or sodium hydroxide because it's a 1-to-1 molar ratio. We used a 1 molar solution and we used 75 mils of it. So 75 milliliters with the 1 molar solution gives us a 0.075 moles of either one. And so I just have to divide my 4.1 by 0.075, and there's my magical number that you remember. Again, they're around in the 50s. And make sure it's negative because the temperature did go up. It's an exothermic process, so it's negative 55 kilojoules per mole. Alright. We kept it to 2 sig figs there, the 55, because the enthalpy was 4.1 kilojoules. Part 2. The student assumes that the thermometer and calorimeter do not absorb energy. Does this assumption result in a calculated value that is higher than, lower than, or the same as if it had, as it would have been had the heat capacities of the thermometer and calorimeter been taken into account? So yes, the calorimeter and the thermometer do absorb a little bit of the heat. So if you assume it doesn't, that means you assume the reaction gave off more than it really did. So we need to justify our answer here. So the calculated value is lower, smaller, or less negative as the thermometer and calorimeter do absorb heat, which we ignore. Okay, so we're assuming that all that heat that we measured came from the reaction, but in fact there was some more that actually went into the calorimeter and thermometer. So our calculated value is lower than what it actually is. And lower, you could say smaller or less negative. There was actually more heat released, but some of it was absorbed by the thermometer and calorimeter. Sorry, you got to scroll back up. Part 3 says, one assumption in interpreting the results is that the reaction between hydrochloric acid and sodium hydroxide goes to completion. Justify the validity of this assumption in terms of the equilibrium constant. Boy, is this a tricky one, but not impossible, and it's a good point to remember. Yes, it's a strong acid, strong base, and you want to say that, the strong's completely ionized, so all the hydrogens and hydroxides would form water, but it says in terms of the equilibrium constant. And you look up here and you don't see any K values or anything like that, so they're asking a lot of us here. It's a tricky point to get, but if you think, what is the net ionic equation? Sorry, I went past. What's the net ionic equation for all of our strong reactions? Strong acid, strong base, neutralization reactions. It is hydrogen plus hydroxide makes water. And what that is, I know we're reaching here, it's the reverse of the self-ionization, Kw. So K for neutralization is the reciprocal of Kw. So our Kw, of course, is 1 times 10 to the negative 14. So all of our all of our K values for strong neutralization reactions, because the net ionic is hydrogen plus hydroxide makes water, is 1 times 10 to the 14th. That large K value says that the reaction goes to completion. Again, a tricky point indeed, but that's something I think you can kind of remember, because all of our strongs, the K is the reverse of the self-ionization of water, our good friend Kw that we know so well from our acid-base unit. Make a note of that. I think that's a good thing to know. And again, tricky point, yes. Attainable, sure. Last part here. A third student calculates a value for the enthalpy of reaction that is significantly higher than the accepted value. What's a specific error in procedure made by the student that can result in a calculated value for the enthalpy being higher than accepted? We're not going to say human error or incorrect measurement or blah blah blah, but what would make it go higher? Well, again, we were reacting our 1 molar HCl and 1 molar NaOH, and as we mentioned earlier, if you accidentally grab the 2 molar, you're going to get more heat. Okay, so if you use your 2 molar solutions instead of 1 molar, that's going to make it go. Now, instead of saying human error, if you specifically said you misread the thermometer, giving you a delta T value that's too high, that's a specific human error that could have happened. So if you specifically mentioned the misreading of the thermometer, or like we said before, if you grab the wrong molarity, a higher molarity is going to give us a much higher amount of heat released. And now this last part says, explain how the error that we just identified leads to a calculated value being too high. Well, again, we're using Q equals MC delta T. So if our delta T is too high, our Q is too high. Alright? And with thinking of that now too, M, if we added too much of our solution, so instead of just doing 2 molar, it said 75 mils. If he, or the student, grabbed 100 mils of each instead, we would also get too high. So it's the M, or our delta T, in Q equals MC delta T, that's going to give us too high of a calculation for our enthalpy. So again, here it says a delta T value too high will result in a larger Q calculation, MC delta T, and of course that's used to calculate our enthalpy change. But again, now that I think about it, if you've included an error that somehow made the M part too big, if you use too much solution, that could also give us a larger Q calculation. Alright, but again, you would have to mention they used 100 mils instead of 75, or they used 80 instead of 75, or something like that. That they might accidentally still plug in 75 here for M, 75 mils, but that of course would also make the delta T higher. So some points to ponder. Again, a nice reflection of a lab that we did in class that hopefully would be helpful here. And again, make note of that, our strong neutralization reactions, acids and bases, their Ks are always going to be 1 times 10 to the 14th, because their net ionics are the reverse of the self-ionization of water. I think that's a good thing. Alright, hope this helps. See you soon.